Okay, welcome to the third virtual lecture for CIS 180 with Messiah College. Today we will be covering the second half of Chapter 10 with operating systems. Remember on Tuesday that we covered the basics of operating systems, examples of how they might appear in your world, the purposes that it covers, the responsibilities that it has in managing both the programs in memory and the processes currently being executed, as well as managing the mappings between logical or virtual addresses and the physical addresses within memory. Today we're going to cover a couple different types of memory management techniques for handling those programs in memory and the data they operate on, as well as touching on the basics of process management for keeping track of any processes currently being executed on your system, in addition to a couple techniques for managing the CPU schedule to determine what process gets to use the CPU next and in the most efficient manner. So let's dive in. The first memory management technique is called single continuous. So the idea here is that memory is basically consolidated into one single continuous block that a program can utilize for storage. We would call this a partition. So one program is one uninterrupted block of memory. It has the whole thing. Address binding is very simple in this configuration. Each logical address is simply represented as an integer value, which tells you how far into the block that given value is found. So if you have an operating system that takes up memory addresses 0 through 24, and your application program starts at address 25, then every other physical address for your system will start either at 25 or 26 or 27. So your logical addresses can be 0, 1, 2, 3, or 4. So if your program starts at address 25 and your logical address is 4, then you simply add 25 and 4 to get your physical address, which would be 29. So it's very, very simple to represent in an operating system. There are a couple pros and cons to this arrangement. The first is obviously its simplicity. It's very, there are no strings attached, there's no hidden little gotchas. It's very simple, very straightforward. The con for this, however, is that because it relies on a program being given uninterrupted access to the memory, it becomes very complex very quickly if you try to load more than one program into memory at a given point. Kind of defeats the purpose. You also end up with a lot of wasted space simply because it is so demanding. If a given program does not completely use up the entire memory space, then that memory is just sitting there being wasted, not being used for anything. So these are the trade-offs that you would encounter. Obviously, for simplicity, you could end up encountering a lot of waste. So to address the waste that is an issue for single continuous, we come up with memory. Partition memory management, which basically says instead of having multiple or having a single program in a single partition, we're going to have multiple programs in multiple partitions. And two methods to make that happen are either setting up your partitions by fixed size or dynamic size. So fixed partition is when the operating system divides up the different memory blocks according to one size. Most of the time they're all the same size, but it really is up to the operating system to determine what the blocks are going to be. They could be different sizes, usually they're the same size. So in this graphic, if the different colors of the programs tell you different sizes, then you can see program 0 and program 3 are in partitions of the same size, whereas programs 1, 2, and 4 all have unique sizes for their partitions. When the computer starts up, your partitions are determined, and after that, they are fixed. They cannot be changed. Dynamic partitions are when the operating system just carves up memory as necessary when programs are loaded. So this means that any available memory that can be used can be reallocated as necessary. In this example here, when program 3 and program 1 complete, their memory spaces just leave a hole. It's open. It's able to be reused. If you have fixed partition management, then those allotments remain that same size. If you have if you have dynamic partition, then maybe program 3, which left a rather larger hole in the memory, might be divvied up to accommodate 2 new programs. So in this situation, you end up with a much more efficient memory management technique, because you are able to cut down on the waste and only giving a program as much memory as it needs, versus fixed partition memory management, which suffers from the same drawback as single continuous, in that if a program does not take up the whole memory size of the partition, you end up with wasted space. Both partition memory management techniques require a little more information than just an offset, as single continuous uses. For a given memory block with different partitions, each partition will keep track of its starting location in what is called the base register. So if you remember back to low-level programming, we had a number of different registers that we used. We had the instruction register, we had the program counter, we had the accumulator, and they're basically just very small, specifically purposed places in memory for us to store information. So the base register for a given partition holds the starting address for that partition, and then the bounds register for that partition will tell us how long the partition is, how many memory spaces it covers. So that way we can calculate what a given physical address is going to be based on an offset within a partition and the base register, the base address for that partition. So starting at memory space 25, again, if your offset is 4, as long as the offset does not overstep the bounds of the partition, then we can return 25 plus 4, which is 29. Okay, so if you have a number of different partitions, how do you decide where to put a program if you're loading it into memory? We have 3 different possibilities here. So let's take a look at this graphic. So in our graphic, we have a new program to load into memory, and let's say it is 16 megabytes in size, and we need to find where to put it in memory. So the first option would be to find the very first partition from the beginning of the memory array that is big enough to hold it. So in this case, that would be the third memory space from the top that is 22 megabytes in size, and that would give us what is called the first fit. So by putting our 16 megabyte program into that 22 megabyte spot, we now have leftover of 6 megabytes, which is kind of small. It's not unusable, but it is kind of small. So to consider it waste, it's not necessarily waste. It depends on the size and the programs that you are going to load. The second method is this concept called best fit, which says I am going to put my program into the smallest partition that is still big enough to hold it. And the idea here is to cut down waste as much as possible. So with best fit, we would use the fourth memory space from the top, which is 18 megabytes, which gives us a leftover of 2 megabytes, which unfortunately, little too small to hold anything. Definitely wasted space. The third option is an interesting one. It's called worst fit or next fit. So the idea here is take the absolutely biggest partition available in the memory space and put my program there. It's a little counterintuitive, but the idea here is that if I use the absolute biggest partition, then I run a much, much better chance of the leftovers still being big enough to be used. So in our case, it's the very last partition in the memory array, 36 megabytes. And by putting our 16 megabyte program into that space, we have a leftover of 20 megabytes, which is still plenty big enough to hold another program. All right, for fixed partitions, first or best fit are your better options because they cut down on any space, they cut down on the necessary leftovers. With fixed partitions, you can't change, remember, the size of the partition. So you just have to do your best to minimize the amount of leftovers that are inevitably going to happen. If all of your partitions are the same size, then first fit and best fit will give you the same results. Remember, with fixed partition, they're not necessarily the same size, but you can't change them. For dynamic partitions where you can change and reallocate partition space, then worst fit is your best option because the remnants left over are much, much more likely to be usable. Okay, so when a process ends and the computer doesn't need it anymore, we can unload or remove a program from memory. So in that case, then the partition is deleted and the space is reabsorbed into the memory array to be used for more program storage. If you are using a fixed partition, then the bounds don't change. If you're using a dynamic partition, then the partition space is completely absorbed into the ones around it to provide a bigger open area for new programs. Okay, so while partitioning is still better than single continuous, it's not ideal quite yet. So paged memory management is basically fixed partition's older brother. Paged memory management allows us to divide our programs up into chunks and then store those chunks instead of trying to find space for a whole program all at once. So for simplicity, we'll assume that these chunks are all the same size. So we call these chunks pages, and we call their storage locations in memory frames. So a page is a chunk of a program, and a page is loaded into a frame, which can be anywhere in memory, either stored completely out of order, anywhere we want, mixed in with other pages from other programs. It could be anywhere. And we keep track of where everything is with what are called page mapping tables, which tell us which page is stored in which frame in memory. Now, if we look at this graphic on the right, we can see that program 1 has 5 pages worth of storage, and program 2 has 4, and the mappings are listed there for you. They're completely mixed up in memory. We have no order to them at all, but because the page mapping table is there, we know exactly where to go to get the data out that we are interested in. So what would it look like if we were trying to use logical addresses to find data? So let's say that the pages are 1024 bytes in size. It's a large program, so the pages are large. So we need to find a given variable within a page of our program. Now, a variable is going to be a much, much smaller portion than 1024 bytes. If you have an integer and the integer is 2 bytes long, then you need to find those 2 bytes somewhere within over 1,000 that are just within a single page of your program, let alone the whole thing altogether. So the way that we refer to this is by a combination logical address. The first term is the page number, and the second term is the offset. So if we know that the variable is in page 2, then the page value would be 2. And if we know that the value of our integer starts at the 518th byte, then the logical address would be 2, 518. And the computer would be able to look up the corresponding frame according to page number 2, and it would go to memory spot 15, and it would dig through all of the data stored in that location until it finds the 518th byte, and then it would return the data as requested. Now be aware that because we have 2 different terms in this logical address, we have to make sure that both are valid. We have to make sure that the page is actually available within the program, within our mapping table, and that the offset does not overflow the bounds of a given page size. So need to make sure that all of that is good. But other than that, page memory management, definitely an improvement over standard partition memory management. Cuts down on waste at the expense of a little more complexity. Now, paged memory management is great, but it could still use some improvement, especially with trying to load very, very large programs. There's just no need to have that all in memory when you're only going to be using a portion at a time. So the idea here is you can improve on paged memory management with the concept of demand paging. So if you are running the CPU, running a process in your CPU, and it's attempting to bring data into the cache from main memory, then we're only going to bring the pages of a given program from main memory into the cache when we need them. So if the program has 500 pages and we only need page 3, then page 3 is what is brought into memory, and the rest of it can stay in main memory until we need it. So if the operating system is requested to bring in page 3, it checks to see if that exists in the cache yet, and if it doesn't, then it will go to main memory to find it. We can also use this concept of page swapping. So a new page is only loaded into memory when the original can be put back into memory. So basically just swapping out an old for new, very standard. This helps to save on memory space because you're only going to use enough memory for the data that you actually need right now. And yes, demand paging can be very powerful, but really it operates on this concept of what is called virtual memory, this illusion that we give to the CPU that there is no restriction on program size, that it can be running for forever because all of this information is in memory and it can access it at any point. But in reality, only a small portion of the program is held in usable memory at any given point, and the operating system is in charge of swapping that in and out for the CPU to use. But it at least gives the impression that there is no restriction. All right. Unfortunately, virtual memory and process management, program management in general, comes with a lot of what is called performance overhead, but basically means that we're spending a lot of resources processing instructions rather than actually completing the calculation or the task that the instruction actually says to do. So that introduces the concept of what is called thrashing, which means that your computer performance suffers greatly because you are constantly swapping out supporting information rather than actually doing the instruction process itself. Okay, so those are your memory management techniques, and we're now going to move on to process management. Process management is a relatively straightforward process. It basically means just keeping track of what is running right now and what state it's in. So there are a couple different process states that are available to us. When a program is loaded into memory and we're getting ready to execute it, it's considered a new process. We're executing, it's brand new, it's admitted to the queue of processes ready to be run, and when it's all ready to go, it is now in the ready state. From the ready state, when a process is given control over the CPU, it is now considered running. When a running process either encounters a memory or user input-output event, or gets to the point where it's stalled, where it's waiting on somebody else to perform a task for it to continue, it is now put in the waiting state. When that event completes, when it retrieves the value it wants from memory, or when it performs its output to the user, it is now back in the ready state, waiting to get the CPU again. It is also possible that an active process that is using the CPU can be hijacked, so to speak, by the operating system and told or forced to give up the CPU, in which case it just jumps directly back to the ready state in order to wait for its next turn with the CPU. Now this loop can happen many times, but as long as the process has not errored out, it will continue to cycle back between ready, running, and waiting until it has completed everything that it intends to do. Once a process has completed all of its tasks, it will exit and enter the terminated state. Okay, so we use what is called a process control block, or a PCB, to manage all of the relevant information for a given process. The operating system maintains what is called a queue for each individual process group, for the state group. So there's a queue for all of the processes that are waiting for I/O events. There's a state queue for all of the processes that are ready, that are just waiting for their turn to use the CPU, etc., etc. The information in the PCB, in the process control block, allows the operating system to set up the necessary environment for the process to run when it's its turn to run. So that would include any register information, such as the program counter, to tell the CPU what instruction to execute next, which will be different for every process. Whatever value was in the accumulator, which will again be different for every process. It also includes any memory management information, such as base or bound register values, page tables, anything like that. And then additional just administrative information, such as time logs, any metadata, things like that. So if you are loading a new process into to be used with the CPU, then the register values that are utilized there have to be those registers, the program counter, the accumulator, etc., are all shared between the different processes, but their values need to be updated when a new process takes control of the CPU. And that process is called context switching. I believe there was a question on the quiz that talked about if an operating system forces a process to give up control of the CPU, what is that called? And we're going to talk about that on the next slide. But context switching is simply the process of overwriting the values that were in the register. When a CPU is actually forced to give up the operation of a given process, that is preemptive and non-preemptive scheduling. It's the active participation of the operating system to determine whether or not a process can be interrupted. With preemptive scheduling, we do allow the operating system, for any given reason, to force a process to give up the CPU. If we use non-preemptive scheduling, it means that a process has the CPU for a given amount of time and cannot be forced to give it up. So for the quiz question, because the operating system was able to go in and force the CPU to give up the force the process to give up the CPU, it's preemptive scheduling. The context switch happens regardless of why or when the process leaves the CPU, but preemptive is when the operating system specifically says you must give this up. So we have a couple different scheduling options here. We're going to talk about first come, first served, which is exactly what it sounds like. Shortest job next, which is also exactly what it sounds like, and round robin. And all three of these algorithms, these methods, will be evaluated by what is called turnaround time. So what is basically the amount of time between a process becoming ready for the first time and when it exits the running state for the last time, meaning once it terminates. So typically the smaller the average turnaround time per process, the better the algorithm. Okay, so first we'll talk about first come, first served, which is a non-preemptive scheduling method. So once a process has control of the CPU, it is simply going to run until it's done. So in this method here, if we have 5 different processes, 1, 2, 3, 4, and 5, the CPU will simply complete that process until it's done in the order in which it receives them. So first 1, then 2, then 3, then 4, then 5. Very, very simple kind of setup here. The time to complete, the turnaround time here, is simply the completion time of the very last process minus the starting time. So P1, process 1, is 140 cycles that it takes. Process 2 is 75, which puts us up to 215. Process 3 is 320 cycles, which puts us up to 535. Process 4 is 280, which puts us up to 815. And process 5 is 125, which puts us up to 940. So the turnaround time, 940 minus 0, is obviously 940. So the average time to complete is all of the completion cycle times divided by 5. So 140 plus 215 plus 535 plus 815 plus 940 divided by 5, which is 529. Okay, so that means that around 529 you hit your middle point. All right, so shortest job next is another fairly obvious algorithm. Processes, again, are non-preemptively scheduled, which means once you get the control of the CPU, you run until you're done. In this method, in this manner, we now have to be strategic about what order in which the processes are scheduled. You can't just put the next one on the CPU as it arrives. So given a set of processes that all arrive in a group, we order them according to shortest amount of time required with the CPU. Now this is an interesting method here. We have the same processes, the same process execution times, but our turnaround is a little different here. The final time on the CPU is still 940, but because the bulk of the completion times happen lower on the scale, the average turnaround time is actually lower per process than before. So we've got process 2 to 75, process 5, which ends at 200 clock cycles, process 1, which ends at 340, process 4 at 620, and process 3 at 940. So 75 plus 200 plus 340 plus 620 plus 940 divided by 5 is an average of 435. So the average turnaround time is almost 100 clock cycles lower with this method than with first come, first served, which was, I believe, 529 clock cycles on average. Unfortunately, this does expect a little more from the operating system. You have to be able to accurately predict the service time required for a given process. We have a number of methods that would allow us to take a guess, but we really have no guarantee that a process is going to take a certain amount of time to complete. If we could know that for certain, this would be the most efficient algorithm to use. But because we can't accurately, reliably predict what our execution times are going to be, we have this concept called round robin. Now, round robin is preemptive, which means that the CPU, the operating system, can interrupt CPU access at any given point. So the idea here is that we are going to chop up execution according to a given what they call time slice, which means that bless me, which means that every interval of time, if a process has not completed its execution, we will force it to stop and move on to the next process. So if, let's say, a slice is 50 clock cycles, then process 1 will not end until time 5:15. Process 2 ends at 3:25. Process 3 ends at 9:40. Process 4 ends at 9:20. And process 5 ends at 6:40. So you can see here that we try to give processes priority in the order according to what order that they arrived in. So we've got 1, 2, 3, 4, 5, and then 1, 2, and at 3:25, 2 ends, so it disappears from the order. So then 3, 4, 5, 1. 1 ends at 5:15, so it disappears from the order. 3, 4, 5. 5 disappears at 6:40, and from there it's just processes 2 and 3 finishing up their execution. Now granted, average turnaround time here ends up being higher than the two methods before. With process times completing so late, we've got 3:25, 5:15, 6:40, 9:20, and 9:40. The average completion ends up being 6:68. Even so, this is the most widely used algorithm because it's the most fair. We don't have any way to predict how long a process is going to take, but we do know the order in which they arrive. So if we give all of our processes equal turns with the CPU, then that allows us to favor or give equal priority to both those processes that arrive early and those processes that have shorter execution times in practice, not just in theory. So if you look at processes 1 and 5, they actually have similar processing times, 140 and 125, but process 1 finishes first because it arrived first. So this really is the best of all worlds, even though it is quote unquote slower. Okay, so that's it for this chapter. Just a quick reminder, be sure to do the exercises from the book, questions 27, 28, 29, and 30, and submit those to Canvas. And have a great week. Enjoy fall break. I will see you on Tuesday. Be sure to do the reading and the quiz for chapter 11. Have a great time. Enjoy your break. I will see you then. All right.